Hello, my name is David, and today I'll be going over the Fourier algorithms and its applications in audio analysis. So to preface, I do not have a heavy background in mathematics, electrical, or physics, but I do have a programming background as a data engineer, and I do have Google. So this presentation will be more of a conceptual overview of some of the most important Fourier algorithms and its applications. I will not be proofing any of the math in explicit details, but I will be explaining the concepts of the math, how it works, and how these Fourier algorithms all fit together. So to begin, I want to present you this picture. You're probably asking questions like, what is this? What am I even looking at? And is that a face? Well, this image is part of the song called Equation, made by the artist Aphex Twins. And no, it's not the album art, but would you believe me if I told you it was part of an actual song? So how is this picture made? The answer is the Fourier algorithms. And by the end of this presentation, my goal is for you to fully understand what this picture is, and more importantly, how it was put together. So who is Fourier, and what is the Fourier algorithms? Joseph Fourier, in the early 1800s, in an effort to investigate how heat transferred in different types of metals, published his results called An Analytical Theory of Heat, and this formed the foundation of the Fourier analysis. Fourier's seminal equations have enabled applications beyond heat alone to almost all forms of science. These applications provide a wide array of analytical and computational mathematics, forming the cornerstone of real-time imaging, audio compression, physics, engineering, and advanced data analytics. Simply put, the Fourier series has had more significant and more profound role in shaping the modern world than any other algorithm to date. Today, I'll be walking through a step-by-step explanation of these Fourier algorithms, starting with his early work on the Fourier series, and then laying brick by brick the foundations, building towards how the Fourier algorithms are used in applications today. We'll start this, our first brick will be the Fourier series, and then how these series are transformed into different dimensional spaces through the Fourier transform. And then we'll also walk how these transformations are applied through the discrete Fourier transform, optimized the fast Fourier transform, and lastly, made useful for applications today in audio analysis through the Gabor transform. Before we dive into Fourier series, I want to quickly review some of the motivations behind the Fourier equations and discuss some of the foundations in which it relies on. To begin, we will start by addressing the environment we're working in. So hopefully up to this point, we're all familiar with finite dimensional spaces. A prime example of this is the Euclidean space, where it is defined as a plane of points that have a relationship in terms of distance and angles. So far, this dimension of space is something we are all familiar with, especially the Pythagorean distance, which, given 2 points, allows us to measure its Euclidean distance. This distance is important because there's really no other natural way to describe the process of adding 2 distinct data points in space. But as we zoom out of this Euclidean space a bit beyond our 2 points, we can see that this Euclidean distance can also be represented as a vector within vector space. I like to think about this relationship in terms of the Latin roots of the term vector, which means carrier, like a ship, horse, or more commonly shown as an arrow that represents something in space traveling towards something else. In other words, given 2 points in the Euclidean space, this forms a vector within vector space. We can also manipulate multiple vectors by adding or multiplying these vectors together, and we call this a dot product of vectors within finite space. Ultimately, these finite spaces give us a coordinate system that effectively allows us to work with scalars and real numbers and the ability to represent a column, row, or matrix of numbers as a geometric object. And hopefully something this is we're all familiar with up to this point. However, a major limitation to these spaces is that when we are faced with modeling a continuous function, which assumes non-linearity, such as music, or really most things in life, and more generally speaking, audio signals. To model these, we need to expand beyond the assumptions of working in finite Euclidean or vector space to allow for the possibilities of where things could be on an infinite scale. To do this, we zoom out again beyond the vector space, and instead of saying point A or vector B is moving in a linear direction, we can describe vector B as a function that has the potential to move in an infinite degrees of freedom or directions with an infinite possibilities of magnitudes. This infinite possibility of movement within space can essentially be mathematically defined as the inner product of a function that takes two vectors and returns a complex number. And that is the general idea behind Hilbert spaces. And so this picture I have here is a artistic rendition of the Hilbert space. No one can really, I for one, cannot really visualize infinite amounts of spaces in my head. So this isn't actually this vector space within an infinite amount of spaces. This is just an artistic rendition to kind of demonstrate how vector spaces fit within an infinite amount of space. So to summarize, by moving from vector space Rvin to a continuous Hilbert space of Dvin, our linear vectors, which we were viewed as ordered tuples in finite dimensional space, can now also be viewed as continuous vectors in infinite space. And this shift in mindset from different spaces we're working in will allow us to really fully understand how the Fourier algorithm works. So, welcome to my Dummies Guide and Dummy series on the Fourier algorithms. To start, we'll first review the foundations of the entire Fourier equations, which is the Fourier series. So what is the Fourier series? Well, it's defined as a way of approximating an arbitrary function f of x as an infinite sum of sines and cosines of increasing frequency. And this is why the Hilbert space, which we just talked about, it really comes into effect, as it allows us to represent this function f of x as an inner product of coefficients within infinite space, which allows us to model essentially curves. These coefficients are decomposed as a sub 0, which is the constant representing the average value of the function in one time period, a of k, which is the function projected into the cosine wave, and b of k as the function projected into the sine wave, and then k being the frequency in which we are summing over from 1 to infinity, where as k increases, the frequencies of sine and cosines also increase. We can also think about this as how much of f is in the cosine function and how much of f is in the sine function, and then we just add it all up at their k frequencies plus the constant. Within vector space, this can also be thought of projecting f of x into cosine k of x and sine of k of x. Mathematically, by looking at how each of these coefficients are calculated, we see that they are essentially integrating between pi and negative pi, which in other words is one time period written as 2 pi. This can be visualized in the diagram right here, where we see the square wave decompose as the integral limits of pi and negative pi. And so in the scenario where we have a perfect Sol wave, which is this wave that we have here, where the coefficients of a and k are 0, what we're essentially doing is we're solving for sine to the nth degree. And so if we look at this formula here, where we have our constant and the sum of our cosine functions and sine functions, in this instance, given that it's a square wave, a of 0 and a of k essentially becomes 0. And so essentially at this point what we're solving for is simply the integral of sine of k. Obviously, there's more complex waveforms, which we'll look into later, but this kind of gives the general idea of how the Fourier series algorithms kind of breaks down. And these coefficients can essentially grow more and more complex and can result in the summation of an infinite amounts of sums. And that is essentially the inner product in which the Hilbert space functions in. So I want to give you guys an actual example of what this k increase in k frequency actually looks like when it looks into modeling a cosine or sine wave, because remember, the Fourier series is defined as an infinite sum of just sines and cosines of increasing frequency. So let me show you guys what this increase in k actually looks like. So let me change my screen here. Give me one sec. Okay, so we have here the code that it gives us essentially a square wave, or at least part of a square wave. And what we see here is we're defining, and this might actually be more useful to pull these up side by side. So we can see here that essentially we have our cosine functions and our sine functions defined, and we're just simply arranging our x and y data to kind of mock up some data to look at it. And we have this variable in, it really is just k. And to implement it, what we're doing is we're summing up all the cosine functions right here. We're summing up all the sine functions over here between a range of k. So as k increases, we're summing it up and we're storing it. And then what we do is we, as part of this summation of the Fourier series, we then add our cosine functions and our sine function coefficients. And so over here, we can see that what we're doing is essentially this part is taking the inner dot product of our cosine and sine vectors. And because it's a square wave, as I mentioned, if I was to look at a of n, which is the cosine function, it's all 0. And so what we're solving for is the sine function. So obviously if I was to print b of n, which is the sine function, we see that they are not 0. But to kind of visualize the increase of frequencies and how it actually plays out is, let's start with a very small frequency value of 2, or I wouldn't say frequency, but as a frequency of 2. We can see that it more or less just gives us a sine wave. And so this is our baseline foundation of modeling this wave this periodic square wave that we have. And so as we increase our frequencies, we can see that our original sine wave now has a bit more squiggles. And so this is kind of the idea where as frequencies increase, it more closely resembles the actual signal or original input that we have originally. And so if I was to, this is k at 5, if I was to make it at k of 10, we can see that the squiggles become more frequent. If I was to make this at 20, we can see that it becomes, and at k of 20, we can see that our frequencies are starting to oscillate that more closely resembles our square wave. And if I was to make this 50, we can see that it closely even resembles it even some more. And so we're looking at k, 5 through 50, but this can be done on an infinite scale. And so as the limit goes from 0 to infinity, what we'll see is that these will more closely converge with the actual square wave that we have. And so let me go back to showing the PowerPoint. So now back to our slides. So to kind of visualize what these increase in frequencies look like, we can kind of see that when we have k equals to 1, in our prior example, what we see is just a sine wave. And so we're seeing that it's just a wave that as it goes through time, it's periodic, which means it goes on forever and ever. It's just a sine wave. And as we increase our frequencies, what it's really doing is it adds another frequency, another wave to the existing wave to kind of model the original, to model our current wave. And this is really, if we think about it, the summation portion of cosines and sines of our Fourier series. So from this visualization, we can see that really there are two apparent truths that reflect the nature of the Fourier series. One is that a signal or waveform is made up of many low-order Fourier coefficients, which is basically our A of k's and B of k's. Similarly, we can also see that the big values that index the higher frequencies, and that most of the signal is made up of low-frequency information. So what we can extrapolate from this is that we can say that these smaller frequencies have a larger absolute value than our higher frequency coefficients. And this concept is important to understand as we move forward and into more complex signals and waveforms, and how we break those down as well. So now that we kind of have a general understanding of a periodic Fourier series, which is applied to the periodic functions, in other words, the Fourier series is a periodic function on a domain. This implies that the functions defined by the series repeat itself forever and ever until infinity. Now, obviously, the same waveform repeating itself again and again isn't very interesting. We can think of this as just a song with only one note being played. I wouldn't really call that song, and I don't really think that song would be too interesting. So what is the alternatives to a periodic function? Well, that would be a non-periodic function, which is also known as an aperiodic function. And these aperiodic functions are essentially functions whose distances between cosine these periodic functions are essentially whose distances between consecutive peaks does not remain constant. And so as a result, aperiodic functions cannot accurately be represented by the Fourier series alone, because if you have a function of non-proportionate periods, such as this one we have here, where you kind of see that it oscillates at this frequency, then it goes a bit higher, and then kind of goes higher, it'll really never converge the same way we see it with a periodic function as the square wave that we just saw earlier. And so it's not to say that you can't use the Fourier series to model aperiodic functions. It just means that there are better ways to do it. Think of it as taking the mean of a random distribution. And so we have a random distribution, and we take the mean, and we say this mean is representative of the whole. That's not a great model or representation, right? We're losing and we're discarding out a lot of the subtleties and nuances. And the same goes for measuring aperiodic signals, where if we try to fit a periodic signal to an aperiodic wave, it's kind of like it's kind of like what we saw earlier, where we would really only be able to look at, where we would only really see this. So this we can see that the sine wave, our periodic signal, would represent this, and we're really losing out on a lot of the other data that we could potentially model. And so this brings us to our next step in the foundations of the Fourier equations, which is the Fourier transform. And the Fourier transform is addressed by many mathematicians as more of an expansion rather than a transformation, as the name implies. However, the general idea of the Fourier transform is that given the time domain function, we can map that function into the frequency domain, and vice versa. And that's done through the inverse Fourier transform, which we'll get into. So essentially, the output of the Fourier transform is nothing more than viewing the original time domain form from a perspective of frequency. And so this allows us to analyze signals, which is hard to analyze, into a signal which is easy to analyze. So in this example here, we take our aperiodic function, which is very difficult to analyze and model because it's aperiodic, and then we can transform it into a frequency domain where it can be more easily analyzable. And this is analogous to a location versus a location address, where let's say I was to give you a location, for example, SMU, you could technically find its location by the name. It's a unique school. And so unless there's another SMU in the world, which I don't know if there is, but you could take that name and you could find its address. Inversely speaking, if I was to give you the specific address, you would also be able to find the name. So if I don't know the address of SMU, but if I was to give it to you, you would probably be able to find the name. Mathematically speaking, what the Fourier transformation is doing is that it takes an aperiodic signal that doesn't repeat itself over a period, And like the Fourier series, it breaks that signal into a series of smaller signals composed of sinusoidal functions. And these series of smaller signals are also commonly referred to as harmonics, which is pretty intuitive. Because if you think about it, a harmony is a signal of as many signals. And when you think of an orchestra, you can think of many instruments and musicians and how it creates a song. And so what the Fourier transform is doing is essentially break down an aperiodic signal into components of smaller frequencies, smaller frequencies. Similarly, if I was to take an orchestra and I was to break it down into its instruments, it's kind of like the same. We can kind of think of it in the same way. And so this decomposition of harmonics is done by first approximating the original signal and simply fitting the curve of that signal. And then recursively, we approximate the differences between each successive curve fit through the approximation of another curve. So we basically have another wave that approximates another wave, and then together we take the sum of all these approximations. We take all of these smaller low frequency waves, and we can fit that. We can fit the original aperiodic signal as a function of frequency. And so you can see how many applications this Fourier transform provides us, as it really allows us to understand the original data by analyzing its frequency content. And so this example I have here, which is made by 3 blue, 1 brown, is kind of a great example of what that breakdown looks like, where we have an aperiodic signal here, and that signal is basically composed of all these smaller signals in time. And so to dive deeper into the math of the Fourier transform, what we really have is two equations, which are the inverse of each other. So we have one that gives us from a time to a frequency domain, and the other one, and the other function, which allows us to go from a frequency domain to a time, can basically back transform it once we are in the frequency domain and we go back in time. And this is really useful when we think about if we take a frequency and we remove frequencies, we can always go back to our original time domain, our original wave, and have the function that we actually want to work with. And this is actually pretty useful for applications such as noise canceling. But these functions are basically composed of two parts: the function signal, which is this, and then the analyzing function, which is the summation of cosines and sine at a point in time. This analyzing function, this e to the I omega t, is essentially Euler's formula, which is also known as the beautiful equation, which allows us to represent the sinusoids as a complex exponential that represents one complex coefficient per frequency. And the whole reason why we're utilizing Euler's formula is because we can technically break down this cosine and sine into its own separate integrals, but utilizing Euler's function, it kind of helps save a few steps along the way in terms of writing it out. So the idea of this inner product between the function and analyzing function is that if we take a complex exponential that has a real function in time and also has an imaginary function in time, which is this I, multiply by a numerical value at omega 1, we get one of the terms in the integral that provides frequency as a measure of time. In a different perspective, if we think of cosine and sine as waveforms, and take a cosine waveform at a particular frequency and a sine waveform at a particular frequency, and we add it all up from omega being negative to positive infinity, this summation of the complex exponentials gives us a time domain signal that we then can multiply by our factor function. So when the value of the time domain signal is similar to the value of the factor function, the resulting coefficient is large. Whereas if the time domain signal, which is represented by this Euler functions, is dissimilar to the factor function f of our original, which is our original function that we're trying to model, the coefficient is small. So in application, what these peaks that we are seeing here in the frequency domain is really how closely the time domain is modeling and approximating. And so at this point, I kind of want to stop and visualize all of the theory that we've been going over and kind of simplify into a single visualization. And before that, So we can see that here we have our original function, f of x, and then we can see that we start breaking it down into its smaller sinusoidal functions of cosine and sine. And then this results in many different smaller low frequency waves, as we have mentioned earlier. And together, when we sum this all up, it eventually gives us our final frequency domain. And the summations of these individual waves provide us the frequency of the original wave, where we can observe the power and more specifically, how often a specific frequency occurs. So in time series lingo, this frequency plot is what is referred to as a spectral density plot. And so when you think of zero frequency in a signal, we know it's automatically an aperiodic signal, because essentially at no point in that signal is there a period present. In other words, at no point in the data does it complete a full cycle. I like to visualize this by, if we were to zoom in infinitely on any of these aperiodic waves, it'll be similar to this fractal image that we have on the right here, where if we keep zooming in and we keep zooming in and we keep zooming in, it basically shows us the same jagged non-repeating waveforms, so on and so forth. And so as a quick aside, fundamentally, this is actually why stocks are very difficult to model, due to the non-stationary, unpredictable nature of it, which makes modeling and forecasting very difficult, because no matter how far we try to break and decompose the signal, it'll always be aperiodic and non-continuous. So anyways, going back to the Fourier equations, now that we have a better understanding of the continuous Fourier transform, we can come to understand that often the data provided to us is not infinite. As a result, in practice, we often don't need to integrate from a continuous range of negative to positive infinity. And instead, we can work within a finite time range. In fact, many times the data we're given is already finite, as we're looking to use the past to predict the future. Or from a different perspective, or from a music perspective, every song has a start and every song has an end. And so up to this point, we've been working with the Fourier transform and the Fourier series within a continuous infinite function, which is great. And that it really sets the bedrock of these equations and how to understand it. But in reality, most things that we have or we're looking at is finite. We were not really looking at an infinite amount of ranges. And so this brings us to the discrete Fourier transform. So what is the discrete Fourier transform? Well, simply put, it's a way of breaking up our continuous Fourier transform from an infinite domain into a finite or discrete ones, thus the name discrete Fourier transform. And this is done by approximating an integral with limits going from negative to positive infinity as an approximation of a finite sum between n to n minus 1. For those that are curious, this approach, by approximating the infinite limits to a finite sum between n to n minus 1 is also known as the Riemann sum, which I really won't go into. So what exactly is going on here behind the scenes? Well, it's actually quite simple. What we can do is we take our original signal in the continuous domain and we divide it into k discrete locations. So think about we have a signal and we break it up. And then along each of these discrete locations of k, we then compute the Fourier transform to get our frequency coefficients. And using Euler's formula, we can then expand that into a sum of sines and cosines. The resulting function becomes a matrix inner product of the input signal f of x and the sample complex analyzing functions. So essentially what we have here is basically the same Fourier transform which we've gone over already. And then we break it up into k discrete frequency bins, and at each nth sampled value, we then basically calculate Euler's formula, which can be decomposed further as our sines and cosines that make up the Fourier transform. However, up to this point, another another limitation arises, as you can imagine, where if we have a number of samples ins as n increases, this can increase at a quadratic scale. So as you can imagine, the computing the discrete Fourier transform, also known as the DFT, just isn't really useful at an application, because as we increase our nth term, as we want to have a finer and finer representations, as we want to break it up finer and finer, it becomes more computationally complex. So what do we do about this? What can we do? What can we do? So this brings us to our next and arguably most famous equation in our walkthrough of the Fourier equations. This equation is considered the top 10 algorithm of the 20th century, and what Gilbert Strang, who is basically just a famous modern mathematician, he describes it as, quote, the most important numerical algorithm of our lifetime. So allow me to introduce you to the fast Fourier transform, and which is more commonly referred to as the FFT. So what is the fast Fourier transform? Well, the fast Fourier transform is one of the most useful and widely used tools in signal processing, digital communications, and is at the heart of modern engineering applications. Without it, we really wouldn't have any streaming capabilities that we have, the ability to send pictures, compression, the list goes on and on. And can you really imagine a life without that? But the basic idea behind this equation is not that hard to understand. The basic idea is that if you have a number of data points in to the power of 2, then the discrete Fourier transform can be implemented much more efficiently, which reduces it down from a quadratic scaling down to a logarithmic scaling. The central idea to this optimization is that a sequence of data points in can be rewritten in terms of 2 discrete Fourier transforms of length n divided by 2. This creates an even index of subsequence and an odd index of subsequence. And through the kind of splitting the discrete Fourier transform into an even and odd, we can then compute these computations in parallel. And so in doing so, what we end up is we have the summation of 2 terms based on the even and odd subsequences, where for each subsequence, the evens contain all the even coefficients, and the odd subsequence contain all the odd coefficients of n data points. At which point, the discrete Fourier transform is then computed at the same time at a much smaller scale. So basically, if we think about it, this function right here, a sub 0 and a sub 1, is essentially very similar to the same discrete Fourier transform we had earlier, where we're essentially breaking up our continuous function into a discrete form, and then we basically optimize this by computing it parallel by splitting into even and odd indexes. But the real beauty of this optimization problem really comes from the ability for it to recursively, continuously split this process for every power of 2, making it, in application, a much more practical computation to utilize, effectively turning what would have been days of computation into merely seconds. And so if we look at this C++ implementation here, we can kind of see the idea of this fast Fourier transform in implementation, where we have a sub 0 being our even index and a sub 1 being our odds. And we can continue splitting this. If I was to write this again and continue splitting it in powers of 2, that's kind of what gives us our logarithmic scaling that reduces the overall time to compute this, what would have been the discrete Fourier transform at a much, much faster time. So now that we've walked through some of the most important equations of the Fourier transform, it's finally time to look into some applications of the Fourier equations. However, unfortunately, to do this, we need to go through another equation that makes this possible. But it's the last one I'll be covering, so stick with me. And this equation is called the Gabor transform. So what is the Gabor transform, and what does it do? Well, it addresses a limitation of the Fourier equations up to this point, including the fast Fourier transform. The limitation it addresses specifically is if we were to observe a signal as a function of time, so let's take our original waveform within time, we have the Fourier transform to give us, to represent that frequency in time within the frequency domain. And then we can also convert that frequency back into time domain through the inverse Fourier transform. But as you can see, this leaves us in a conundrum where we can really only view one domain or the other, not both. We can only look at it through the time domain or the frequency domain. But when it comes to analyzing music or audio signals, we really need to have both components to fully understand the composition of a song. Since a song is essentially, in essence, just an arrangement of different frequencies over time. So the Gabor transform addresses this limitation by essentially enabling us to analyze both time and frequency together. So how does it do that? It's actually quite simple. Instead of computing the Fourier transform over the entire domain of either time or frequency, the Gabor transform makes the Fourier transform a dual function of both time and frequency. Time and frequency. This implementation of this is very straightforward. Well, we take our existing Fourier transform. So if we look at this equation here, or Fourier transform implemented right here, which we've been going through many times. So all we're doing is we multiply it by Gaussian distribution of g of alpha. And this Gaussian sliding window is what gives us a sliding window to be able to compute our Fourier transforms at different time windows. And so what it means is that the Gabor transform is really just, simply put, the Fourier transform weighted by the Gaussian window sliding across time. And so if we can think about it is we have our Fourier transform within time, and then we also have our sliding window. So if we can think of time as the entire continuous range broken up by our discrete Fourier transform, we can then apply a window by finding, using B as a parameter to find how big our window is to analyze that Fourier transform and to get that frequency, to allow us to view both frequency and time. To kind of think about this, the result of the Gabor transform essentially allows us to compute the spectrogram, which essentially is a time frequency plot of what frequencies are active as time evolves. And to kind of view this, I have an example of a spectrogram here. To view this, each vertical strip, so we can kind of see each vertical strip here. This is the original, where we can see there's you can kind of see striations within this as it moves through time. And these are the vertical strips. Each vertical strip is the power spectrum of a short window of time. Thus, these short windows of time is actually why the Gabor transform is also known as the short time Fourier transform, STFT. Very intuitive. And in the spectrogram is we can essentially think of it as we move up in time by flipping it. So if we take this plot and we flip it up and down, which I actually think makes more sense to me, we can see that as we move up in time, each horizontal strip is essentially all the frequencies in that short window. So if we were to go back to our equations, we compute the Fourier transform, we take our time domain, we get the frequencies, and then we can then see the frequencies in time using this Gaussian distribution function, which visualize is basically each of these horizontal strips that we see here. Now obviously, this results in a bit of data loss since we really can't capture the entire resolution, but it does give us a very close approximation that enables us to analyze audio signals quite effectively. In fact, the spectrogram is a very powerful way to analyze data, as it allows us to pull features out of the data. And if you think about it, if you ever use Shazam, if you don't know what Shazam is, it's an app that let's say you're at a bar and you hear a song, you're like, wow, I need to know what this song is. You can just hold your phone up with your microphone, you point it into the sky, and it starts recording. And what it does is it basically is doing a spectrogram where it finds the frequencies of the song you're playing, and then it tries to match it to Shazam's library of known songs, and then returns to you the most similar arrangement of frequencies. Essentially, if you think about the spectrogram, let's say if we have a song that we want, we play it, we record it, we play it, and it gives us all these different frequencies. Well, what Shazam does, it has a library of all of these different spectrograms, and we're essentially just it's a routine of just trying to match our current input frequencies over time with what they have, and it's that essentially returns us the song information that we're looking for. Additionally, given a song, what the spectrogram really allows us to do is it allows us to classify sound, and it allows us to specifically classify instruments, or voices, or in more generally speaking, just any audio signals. And it really gives us a unique signature of that instrument, musician, or signature or audio signal as a frequency. And so, what we can think of if we have a guitar that's playing a certain note, that guitar playing that certain note occupies a certain frequency, or you can think of it as a signature, a unique signature that stays true through all different frequencies. And let me give you guys an actual example of what this spectrogram looks like in application. And so let me once again change my screen over. One moment. So I like to do a bit of music production on the side, and we've been talking about the spectrograms and the frequencies, and the unique signatures and how it looks like. So I want to give you guys an actual live demonstration of what audio analysis can be done in real life using these spectrograms. Now, obviously, I've talked about one with just Shazam, but let's visualize this in real time. So what we have here is a series of chords. In fact, this is, let me just play it to you and you guys can hear it. So let me play it again. So what we have here is essentially notes on a keyboard. And so when we think about it, let's add a frequency. Let's look at this through a spectrogram so we can see in real time what it actually looks like. So spectrogram. And so let's get rid of that. And so now as I play the song, and let me actually change the scale a bit. So this is kind of what I'm talking about, what I was talking about earlier, where we can see where if we map if we were to map our spectrogram to the keyboard, we can see that they essentially line up. If I was to make this the same resolution and size, it essentially overlays so that we can see that each note being played within a chord is essentially represented as frequencies. And so, for example, if I was to play a note like this, we can see that this C4 note is also being represented within the spectrogram. And if I was to play a higher frequency, we can see that it shifts the frequency from a lower frequency to a much higher frequency. But in application, we can also see that it occupies a certain note, which is very useful for decomposing songs, because if we think about it, a song is essentially just a series of frequencies, and so we can really view these. It allows us to view songs in a totally different way and perspective. And so if I was to play this again, so we can see that these frequencies, and I'll demonstrate to you the signature of these frequencies, where right now all we're looking at is just a piano keyboard. If I was to change this instrument by, instead of using a grand piano, we'll use a Rhodes, and we play it again, we can then see how although the frequencies still maintain the same shape, so we can see how the chord progression goes up and then goes back down, the frequencies are not the exact same. They're slightly different because we're using a different instrument. And this idea is kind of what I was talking about in terms of the unique signature of an instrument given its specific frequencies. And so now going back to our presentation, we can see how these transformations, the Fourier transformations, is a very powerful tool. I demonstrated one using in music, an application of music, but there are many other applications. One is image analysis. So you might be thinking, frequencies and images? What does that even mean? To be honest, I still don't fully understand how frequencies work in images exactly. I won't be covering it, but to kind of boil it down, it describes changes in respects to the positions in space. So similar, if we think about a waveform being decomposed as many smaller waveforms, we can think of an image that if you look at it through a telescope or a microscope, you can dial in on how accurately you want to see it. And so if we can kind of see that we have this original image here, and then as we add additional frequencies, and after about half the frequencies, it can kind of comprise most of what this original image is. And so this is very useful in neural network models, specifically CNNs, where we're working with images, where the CNNs are using fast Fourier transforms, and using that to increase the computation of these CNNs, where as we increase the number of filters in our convolutional neural networks, using a fast Fourier transform, actually it speeds up the overall computation time by decreasing the number, or by reducing the number of steps used to get fast results without altering the accuracy. And so if you can think about it, when we think about the Fourier transform within a signal wave or in a signal domain, the fast Fourier transform was essentially breaking down recursively our discrete Fourier transform and saving a lot of time there by recursively splitting it into smaller and smaller problem sizes. The same can be applied to images as well, and so that's another application of the fast Fourier transforms. There's many other applications, but I won't go through all of them. But I think these two are some of the most applicable in my perspective at the current moment. The fast Fourier transforms is used in many different disciplines of electrical engineering, in physics, in biology, but these two are ones that are most familiar with, that I'm familiar with. And so in summary, we can see that the Fourier series, in summary, is essentially we're viewing a signal in time as an infinite sum of sines and cosines of increasing frequency. The Fourier transform maps that Fourier series in time into a function of frequency, vice versa, through the inverse Fourier transform. The discrete Fourier transform takes our Fourier transform and breaks it up into discrete segments, which makes it more within finite space to make it more, which fits a more realistic problem case. And then the fast Fourier transform essentially optimizes that discrete Fourier transform by recursively minimizing the problem size. And then the Gabor Fourier transform allows us to view this fast Fourier transform in both time and frequency. And together, this allows us to view and analyze audio signals as through the spectrogram, utilizing the Gabor transform. So going back to our original pictures that I showed at the beginning, we can see that this, if I was to break the equation, the song equation by Apex Twins, we can see that this is essentially just a spectrogram, and that it's really, though this image at first seems very complicated, we can see that what these what each window is our Gabor transform, which is a sliding window of time of different frequencies. And so if this was the song, this is just a frequency in time of that song. And so what this artist did was he basically found frequencies and very artistically then kind of stitched it together to formulate an image. So in conclusion, we've gone through the Fourier, most of the more popular Fourier algorithms, from the Fourier series to the Fourier transform, to the discrete Fourier transform, the fast Fourier transform, and Gabor transform. And hopefully we can better understand how we can take a signal and decompose it and allow that decomposition of signal into many applications that we can then use. So thank you for your time. Thank you for listening to me. I hope you enjoyed it.